Okay, I want to make sure that we cover changing the equation of a line to function notation. It just means that once you find the equation of the line, given this point and this slope, you just change it to the function notation we were talking about, f of x. So this says write an equation of a line that passes through the point 2, -3 and has slope -4. To write that equation, you're just going to say, all right, y equals mx plus b. That is the equation of a line. We know our m, that is -4, so y equals -4x plus b. To find out what b, the y-intercept is, we can just use this point that they gave us and plug in -3 for y and 2 for x, and then figure out what b is. So that's -3 plus 8 is going to be b, so b is 5. So you write the equation of the line y equals mx plus b, and since you want to write it in function notation like that, you just change the y to f of x. And now it looks like a function. All right, talking about another way to understand slope of a linear function is to understand it as a rate of change. So if you look at this line on the left, as you're going from left to right, traveling along the x-axis horizontally, you're looking at the rate at which y is changing. You can kind of think of it as the rate at which this line is rising up from 0. So it's starting out at 0 over here. You're moving along the x-axis. It's going up kind of slowly. It's just increasing, and we call that increasing, an increasing function. As you go from left to right, it's getting bigger, but it's not getting bigger very fast. So it has a slow rate of change. Over here, as you go from left to right, again, always left to right, you notice that it's at 0 here, and then by the time you get just this far, it's already way up here. So it has a faster rate of change. And when we talk about what's changing, we're talking about y. As we go along the x-axis, y is changing rapidly. It's getting bigger, faster than this line over here, which is y is getting bigger more slowly. Now, sometimes you want to know the average rate of change on something that's not a line, maybe a curve or something like this that's just curve-ish. And you can't find the overall rate of change on a curve, but you can find the average rate of change on a piece of a curve. So you often want to do that. So like here, you've got the world population growth from 1750 and then predicted to 2150. And you can see that the average rate of change from 1750 going to maybe 1900 is pretty slow. It's not changing very rapidly. And then suddenly from 1950 to 2000, it just shoots up very quickly. And you might want to know, well, what was the average rate of change between 1750 and 1850? And so you would draw a line through those 2 points on the function. Now that line is not exactly the function because the function is curved, but it will give you the average rate of change if you find the slope of that particular line. So to find the slope of that line, you would just take the difference in the y's. So 1200 minus 800 over the difference in the x's, 1850 minus 1750. And so that's 400 over 100, which is 4 over 1. That's the slope of that line right there. And that would tell you, okay, from 1750 to 1850, the rate of change of the world population was about 4 million people per year were being added to the population. You could look at, different intervals on a curve and find the average rate of change for those intervals, but you can't find the rate of change over the whole curve because it's not the same all the time. So the bottom line is that when you have a curve and you want to know the average rate of change on a certain interval of that curve, all you need to do, and you draw a line between those 2 points, and then you find the slope of that line, and that line is the average rate of change on the interval from x sub 1, in this case, to x sub 2. Okay, so here we have a parabola, f of x equals x squared minus 1, and we want to determine the average rate of change as you go from x sub 1 at -2 to x sub 2 at 0. So as you go from here on the x-axis to here on the x-axis, what is the average rate of change of this parabola? What is this parabola kind of doing? How fast is it increasing or decreasing? What's it doing? And so to figure that out, all you have to do is draw the line that goes through those 2 points and find the slope of the line. And so that's just going to be y1 minus y2, or y2 minus y1, either way, over 0 minus -2 in this case. So you've got -4 over 2, which is -2. So the average rate of change of this parabola on the interval from -2 to 0 is just -2. That's what you would say. Okay, here you have a situation that's very simple algebraically, which you've done these kinds of equations many times, but we're going to talk about how can you find the solution sets to these equations and inequalities just by looking at a graph. All right, so in the first part, in part A, you've got 2x minus 3 equals x minus 1, and you want to know the solution to that equation. Well, you know how to do that algebraically. All you have to do is subtract x on both sides, and you'd have x minus 3 equals -1, and then you add 3 on both sides, and you'd have x equals 2. That's the solution. But we don't want to think of it algebraically. We want to think about it graphically. So graphically, on the left side of this equation, you have this line, y equals 2x minus 3. That's the blue line in this picture. It's the line that has its y-intercept at -3 and has a slope of 2, up 2 over 1, up 2 over 1. That blue line, we want to know when does it have the same value? When does that function have the same value as this other line, the y equals x minus 1, the purple line? That is the line that has slope 1 and has a y-intercept of -1 right there. So if you're asking when is 2x minus 3 equal to x minus 1 in this graphic way, then you would just say, well, it's when they cross, because it's when they have the exact same value, is right there. So that is when x equals 2, which we already found algebraically. But looking at the picture, you can also see that these two lines have the same value when x equals 2. They both have the value of 1. On part B, you want to know when is 2x minus 3 less than x minus 1, which is basically asking the question, if you're talking about the graphic question, it is asking when is the blue line below the purple line? When is 2x minus 3 less than x minus 1? So if you look at the picture, the blue line is below the purple line in this area. And the question is, well, what values of x are you talking about? You're talking about all the values of x up to 2. So as you're coming along from left to right, that blue line is below the purple line until you get to x equals 2. And then that blue line is above the purple line. So the solution to that second inequality is going to be from -infinity up to 2, not including 2, because that's when they're equal. And if you were to solve this inequality algebraically, you would subtract x on both sides. You'd have x is less than, you'd add 3 on both sides. You'd have x is less than 2, which is exactly what we just got. So we're talking about how, this is called analytic geometry, this whole xy plane thing where you take an equation and you make a picture of it, a line or a curve or something. This whole idea is that there's an algebraic way to look at things, just using symbols, and a geometric way to look at things. And that's when you have graphs. Then on part C, you've got 2x minus 3 is greater than x minus 1. That means when is the blue line above the purple line? When x is bigger than 2, the blue line is above the purple line. The blue line has a value that is greater than the purple line. So 2x minus 3 is greater than x minus 1 when x is greater than 2. And that's what you'd find out if you subtracted x on both sides and added 3 on both sides. You would get x is greater than 2. So this is just talking about the relationship between the algebraic point of view and the geometric point of view. You can look at these things in more than one way.